TechDaily.ai, your source for technical information. This podcast is sponsored by Stonefly, your trusted solution provider and advisor in enterprise storage, backup, disaster recovery, hyper-converged in VMware, Hyper-V, Proxmox cluster, AI servers, SA365, a turnkey security appliance, and public and private cloud. Check out stonefly.com or email your project requirements to sales@stonefly.com. Okay, let's dive right in. You're writing code, maybe a slick Python script or some Java, right? You hit run and bam, your creation comes to life.
Yeah, it just works.
But have you ever paused and thought, wait a minute, how does this jumble of characters actually become something my computer understands? It feels almost like, well, like magic, doesn't it?
It absolutely does. And, with our modern IDs and tools handling so much behind the scenes, that sense of magic can actually hide what's a really fundamental and fascinating process.
Right.
So the goal of this deep dive is really to unravel that mystery. We want to understand the incredible journey your code takes, from the human-friendly language you write to the ones and zeros that actually make your computer tick.
Exactly, because when you peel back the layers, you find that there are really two versions of your program running around.
That's a good way to put it.
First, there's what we all know, the source code. This is where we get creative, naming variables, structuring logic with if statements, loops, organizing our thoughts into functions. It's the version we can actually read and debug.
And share with other people, yeah. But then, sort of lurking underneath, is the machine code.
Ah, the mysterious part.
Right. This is the computer's native language, specifically the processor's language. Think of it like a very, very long list of instructions, but they're all in binary, just ones and zeros.
Ones and zeros.
And at its core, a processor's world is surprisingly simple. It can read data from memory, it can write data to memory, and it can do some basic math. That's pretty much the toolkit.
So everything we see, complex games, simple text editors, it all boils down to just reading, writing, and calculating. That's kind of amazing when you think about it.
It is. And that executable file, you double-click. It's essentially just that meticulously ordered list of binary instructions.
Telling the processor exactly what to do, step by step.
Exactly. Tiny steps like grab these bytes from memory, add this number to them, put the result back here, or maybe, if this little flag is set, jump way down the list to a different instruction.
Okay, so how do we get from my readable if statement to that? There has to be a bridge.
There is. And that bridge is the compiler. Think of the compiler as this incredibly complex machine. Well, it's actually software itself whose entire job is to span that gap.
The translator.
Precisely. It takes the human-readable source code and turns it into the computer-readable machine code.
So where does this compiler even begin? It gets my file, which is just text. Then what?
Well, it works in stages. The very first thing it does is break down that text, that string of characters, into meaningful units. We call them tokens.
Tokens, like words.
Kind of like words, yeah. It identifies keywords like int or while, variable names you've made up, operators like plus, or even punctuation like semicolons. Each one becomes a distinct token.
Okay, I can picture that. It's chopping the sentence into individual words and symbols. What's next once it has this, bag of tokens?
Next comes parsing. The compiler takes these tokens and figures out how they fit together grammatically according to the rules of the programming language.
Ah, the grammar check.
Exactly. It organizes them into a structure, often called a parse tree or abstract syntax tree. This helps it understand the relationships like this variable is being assigned this value or this expression is the condition for this if statement. It's about understanding the structure, not just the individual pieces.
So it's building a blueprint of the program's logic. Got it. What else?
After parsing, it does something we can call contextualization. This is where it records important details. It notes down variable names and their types as X and integer. Is name a string? It records function names and how they're supposed to be called.
So it's building up its knowledge base about my specific code.
Right. In a simple example, if you have int x, the compiler remembers, okay, x exists, and it holds whole numbers. This context is vital for checking errors later, like if you try to multiply a number by, say, someone's address. The compiler uses this context to say, hold on, that doesn't make sense according to the rules.
Okay, that makes sense. It's cracking everything. Then comes the magic part. Right. Turning this understanding into actual machine code.
Exactly. That's the code generation phase. The compiler essentially walks through that structured parse tree it built. For each part of your original code, each statement, each expression, it figures out the sequence of low-level machine code instructions needed to achieve the same result.
Okay.
Now, it's worth mentioning this is a slightly simplified view. There are often intermediate steps, intermediate languages, and lots of optimization that happens here to make the code run faster or use less memory. But the core idea is translating the structure into machine instructions.
Okay, let's get practical. Let's use a super simple example. Say I write int x equals 3. That's it. What does the compiler do with that text?
Okay, so first, as we said, it tokenizes and parses. It understands you're declaring an integer x and assigning 3 to it. Then in code generation, it needs to make that happen in machine terms. It might produce something equivalent to this assembly code instruction. Move 3, memory location for x.
Whoa, hang on. Assembly code, that looks different. Still not ones and zeros, but closer.
Exactly. Assembly is a low-level language, but it's more human-readable than raw binary. Think of it as a mnemonic representation. Each assembly instruction typically corresponds directly to one machine code instruction.
Okay.
So move is the instruction name, 3 is the value, and memory location for x signifies a specific spot in the computer's memory that the compiler has decided to use for storing your variable x.
So the compiler picks a memory address for x.
Yes. It manages memory allocation. So that simple line xl3 becomes an instruction telling the processor, take the number 3 and put it into this specific memory slot.
Wow, okay. So every variable gets its own little patch of memory managed by the compiler.
Essentially, yes. Now let's make it just a tiny bit more complex. What if we add x equals x plus 1?
All right, so we declared x, set it to 3, now we're adding 1 to it. How does that translate?
The compiler would likely generate a different instruction, maybe something like add 1, memory location for x.
Okay, that seems logical.
This tells the processor, go to the memory location for x, take the value you find there, add 1 to it, and then store the new result right back into that same memory location. It's directly manipulating the value stored for x.
It's fascinating how these high-level ideas, like adding 1, become these concrete memory operations. It really does pull back the curtain. But what about things like if statements or while loops? I don't see an if instruction in your assembly examples.
That's a really sharp observation. You're right. Most processors don't have a single machine instruction that directly maps to an if or while or a function call.
How did they work then?
The compiler has to be clever. It simulates these higher-level structures using the basic instructions it does have, mainly involving calculations, comparisons, and crucially, jump instructions.
Jumps, like skipping parts of the code.
Exactly. Let's take your if. Say you have if score 100. The compiler first generates machine code to evaluate score 100. This might involve loading score from memory, comparing it to 100.
Okay.
The result of that comparison sets special little things in the processor called flags. Think of them as single bits, remembering if the result was greater than, less than, equal to, etc.
Got it. Tiny status indicators.
Right. Then the compiler uses a conditional jump instruction. It essentially says, check that flag. If the flag shows the condition, score 100 was false, then jump over the next block of instructions.
Ah, so it skips the do something part if the condition isn't met.
Precisely. If the condition was true, the jump isn't taken, and the processor just continues to the next instructions, which would be the code for do something.
Okay, that makes sense. It's creating a detour in the instruction list based on the condition. So what about if else?
Builds right on that. You have the conditional jump to skip the if block if the condition is false, just like before. But then, right after the machine code for the if block, the compiler inserts an unconditional jump.
Unconditional, so it always takes that jump.
Yes. That jump skips over the machine code for the else block. So think about it. If the condition is true, you execute the if block, then hit the unconditional jump, which skips the else. If the condition is false, the first conditional jump skips the if block, you land at the else block, execute it, and then just continue on.
Clever. Using 2 jumps to make sure only one path is taken. Okay, what about loops? Like while condition. Repetition seems different.
It uses a similar trick, just looping back. For a while loop, the compiler will typically 1. Put the instructions for the loop body in memory. 2. Before the body, put instructions to evaluate the condition. 3. After evaluating the condition, use a conditional jump. If the condition is false, jump past the loop body and then jump at the end. 3. After evaluating the condition, use a conditional jump. 4. Right after the loop body, put an unconditional jump that goes back up to step 2 to reevaluate the condition.
Whoa, okay, so it checks. If true, it runs the body, then jumps back to check again. If false, it jumps out of the whole loop structure.
You got it. That creates the repetition using only comparisons and jumps.
And functions, they seem even more complicated, needing to remember where to return to.
Functions involve a bit more housekeeping, definitely. When you call a function, the compiler generates code to basically save the current state. This includes the address of the next instruction after the function call so it knows where to come back to,
Where does it save this?
usually on a special area of memory called the stack. It pushes the return address onto the stack. It might also save current values from processor registers. Then it allocates new space on the stack for the function's own local variables.
Okay.
Then it jumps to the machine code for the function. When the function finishes, it generates code to clean up its local variables from the stack, retrieve that saved return address, and then jump back to that address.
That whole process enables functions and even recursion, right? Because each call gets its own saved spot on the stack.
Exactly right. Each call is independent because its context is saved separately. It's quite an elegant system all built from those basic instructions.
It really is. But it also sounds like this generated machine code must be super specific to the computer it's running on.
Absolutely. That's a crucial point. Portability. Machine code is fundamentally tied to the processor's architecture, Intel, ARM, etc., and often the operating system too.
Why the OS?
Because programs need to interact with the OS for things like reading files, network access, drawing windows on the screen. The way you ask Windows to do that is different from how you ask Mac OS or Linux. And the processor instructions themselves are just different. An instruction encoded for an Intel chip is just gibberish to an ARM chip.
So if I compile my C++ program on my Windows machine, I can't just copy the executable file to a Mac or a Linux box and expect it to run.
Nope. Generally, it won't work. The machine code is incompatible. You'd need to recompile the source code specifically for the Mac with its processor and OS, and again for Linux.
That sounds like a pain for developers who want their software to run everywhere.
It is. And for a long time, that was just the reality. You created different versions for different platforms. But this challenge led to some clever solutions.
Like what?
Well, one major approach is using an intermediate representation. You might have heard of bytecode, especially with languages like Java.
Java, right. I've heard of the JVM, the Java Virtual Machine. How does that fit in?
So instead of compiling Java source code directly to, say, Intel machine code or ARM machine code, the Java compiler compiles it into this intermediate format called Java bytecode.
Okay, so it's not machine code for any specific processor.
Correct. It's a generic instruction set. Then, to run the Java program on your specific computer, you need the JVM. The JVM acts as an interpreter, or more often these days, a just-in-time JIT compiler. It takes the bytecode and translates that into the native machine code for whatever processor and OS you're actually running on right when you need it.
Ah, I see. So you compile once to bytecode, and then the JVM on each different machine handles the final translation step.
Exactly. Write once, run anywhere. That was the promise.
Yep.
You get portability.
Is there a downside? Does it run slower?
There can be a performance cost, yes. That extra step of interpretation or JIT compilation at runtime can introduce some overhead compared to running code that was already compiled directly to native machine code ahead of time. But for many applications, the flexibility and portability gained are well worth that trade-off. Modern JIT compilers are also incredibly sophisticated and can optimize code very effectively as it runs.
It's just amazing thinking back, comparing this to the early days. You hear stories of programming and assembly directly, or even flipping switches for machine code using punch cards.
Oh, absolutely. It was a completely different world. You needed intimate knowledge of the specific hardware, the exact instruction set, managing memory manually.
And code written for one computer model was basically useless on another.
Totally incompatible, usually. The development of compilers was truly revolutionary. They are these incredibly complex programs themselves, automating that painstaking translation.
And it's funny, compilers are programs too, right? So they had to be written in something and then compiled themselves. It's like turtles all the way down.
It is. It's a bootstrapping process. Early compilers might have been written in assembly or even machine code. Then, once you have a basic compiler, you can write a better compiler in a higher level language and use the first compiler to compile the second one.
You can even write a compiler for a language in that same language?
Precisely. You compile version 2 of your C compiler using version 1. It's a testament to how software builds upon itself. And think of all the tools that grew alongside syntax, highlighting in editors, symbolic debuggers that let you step through source code instead of assembly, all enabled by this compilation process.
It really makes you appreciate hitting that run button, all that history, all that complexity handled for us.
It's the hidden engine of modern software development. These compilers quietly translate our ideas into the language the machine understands.
TechDaily.ai, your source for technical information. This podcast is sponsored by Stonefly, your trusted solution provider and advisor in enterprise storage, backup, disaster recovery, hyperconverged in VMware, Hyper-V, Proxmox cluster, AI servers, SA365, a turnkey security appliance, and public and private cloud. Check out stonefly.com or email your project requirements to sales@stonefly.com. And just think about that final point programs, creating programs. We use compilers, Brit with code, to turn our source code into executable code, constantly automating more and more with what feels like just a simple push of a button. It's an incredible chain of innovation, really.
TechDaily.ai, your source for technical information. This podcast is sponsored by Stonefly, your trusted solution provider and advisor in enterprise storage, backup, disaster recovery, hyperconverged in VMware, Hyper-V, Proxmox cluster, AI servers, SA365, a turnkey security appliance, and public and private cloud. Check out stonefly.com or email your project requirements to sales@stonefly.com.